Well, good morning, everybody, and thanks for joining. You've got a VNA now. Now, what do we do with it? That's kind of what I'm going to cover here. Now, since the VNAs, vector network analyzers, really are two-port networks, I have to start with describing what a two-port network is and what it does. Without that information, we're not going to do very much. We're not going to make very much progress here. So, vector analyzers, you can buy really expensive ones made by Hewlett-Packard, now called Agilent, or now called some other company. They've changed names so many times. But recently, we've gotten some low-cost analyzers. Some of them less than $50. But what are they, and what do they mean? The one you have may look like the one I have, or it may be something different. You may have SMA connectors on the top here. These may be SMAs. The one that I bought has N connectors on it. It's a little bit larger and comes in a steel case and everything. And that really doesn't matter. But you can measure insertion losses of two-port networks, return losses on coax, reflection coefficients, and then display them all on a Smith chart. And you might ask, what does all that stuff mean? Well, hopefully I can answer all those questions. At the top of your VNA, you've got two terminals. I'll call them, hesitate to call them ports because I'm using that as another term, but they're basically two ports. This is the one we're going to concentrate on. It's the transmit port. This is the receive port. This one sometimes is called S11 on your VNA, and this one may be called S21, but more on that later. I'm going to simplify this actually because we're going to talk about the transmit port. And it's just an ohmmeter on steroids. And that's the way you should think about it. When I say it's on steroids, in the same way that your ohmmeter measures resistance, the TX port of your VNA measures complex impedances, R plus JX, R minus JX, and displays them in a lot of different ways that are intended only to confuse you, but hopefully we can straighten all that confusion out. Anyway, but since an impedance itself can be a function of frequency as opposed to resistance, you do this by setting a frequency on your VNA or a band of frequencies to sweep. So, just like an ohmmeter places a known DC voltage across a resistor and then measures the current, uses a computer to calculate using Ohm's law, and it displays the resistance, you can kind of think of the TX port as the same thing. It doesn't actually do this, so don't call me on it, but you can think of it this way, that it puts an RF voltage out on the terminal, measures the current and phase of the current that it sees, and then calculates the complex impedance in the same way that an ohmmeter does. So let's start by thinking of that terminal only as an impedance meter. You have a resistance meter in your ohmmeter. Now you have an impedance meter that measures complex impedances at any RF frequency that you want. So think of it as an ohmmeter on steroids. Now, before we get into it, and everybody here has at least a technician class license, so I assume that everybody has it, complex impedances that over on this is the complex plane, if you will, and over here, N9GE is calling. I just turned on the radio. Over here, we have pure resistance on this line. Above the line, we represented by positive inductors. On this side, negative in capacitors. So this is R plus JX, and you just read it off the scale. Here's a resistor, say 1 ohm. This is an inductor, say plus J1 ohm. Down here, we have a resistor plus 1 ohm. Down here, we have a capacitor minus J1 ohm. So if you're not familiar with this, you're not comfortable with this, you really do need to go back and review it because it's really, this is what complex impedances are all about. So the generic two-port network, very simple device. It's got an import on one port on the left, one port on the right. Now, we may not know what's inside exactly, but there's a few things externally that we could do to kind of get an idea for what this network does. For example, we could put a voltage across the input terminals and measure the current. Well, that'll give us the input impedance. Or we could put a load on this thing, put a voltage on the input and measure the voltage and current on the output, and then it'll give us some idea of what the transfer characteristics are, or insertion loss, if you will. So what have we got? We've got, you can imagine any kind of little device inside of our two-port network. I mean, it could be infinite number of things. I'm showing two unbalanced things here where the negative terminals are connected. You can also imagine that you can have balanced networks where it's not all ground on the bottom side, but it's a generic set of impedances, and in any configuration. Now, it is really cool, and this is an important point of two-port networks, is that there exists an impedance that if you terminate a two-port network, that impedance will appear at the input as the input impedance. Now, what is that? I'm going to call that impedance Z0 for the time being, but it's worth repeating here because it's so important. If I were to take any two-port network and find some magical impedance here, then we're going to get to what that is. But it's a magical impedance such that when you terminate your two-port network, you get your Z0 appears magically at the input. We call this the image impedance, because when you terminate a two-port network in the image impedance, you magically see an image of that Z0 on your input port. Now, you see, I use the word iterative, and when I was taking a college level course on two-port networks, my professor, and most college professors like to put their own stamp on things, and he always called it the iterative impedance. But you'll see that almost everybody uses the term image impedance when they're referring to the Z0. So what is it? It's got an interesting implication here that I want to point out, is that if we take the same two-port network and we put 6 of them in cascade, we have, and we terminate the last one in the image impedance, then remember what I said, the image impedance appears at the input of this two-port network. And likewise, that means this two-port network is still terminated in the image impedance, therefore the image impedance appears here and all the way down the line. So if we terminate any two-port network and cascade them, if we terminate it in the image impedance, it appears magically as an image all the way down the line. Wow, now that's really cool. And it's something, somebody talking there? Have a question? Okay. Anyway, it's again, this is a characteristic of any two-port network. So how do we find this magical impedance? And it turns out that it's really very simple. We take our two-port, we leave the output terminals open, and we measure the input impedance, and we'll call that Z open or ZOC, open circuit. And then we take the same two-port network and we put a short circuit across the output. And we repeat it. We have an impedance meter now, remember, and we just take our impedance meter and we measure the impedance across the input of that two-port network. Now, it turns out that the iterative impedance, the image impedance, is the geometric mean of those two impedances. Now, what does that mean? It means you just take the product of those two impedances, multiply them together, take the square root, and you got your image impedance. It's that simple. You can measure it, and you do every time you calibrate, by the way, because you by now I think you've recognized the open and short circuit calibration that you may or may not have done on your VNA already. But you have calculated, if you will, the image impedance of the network. So You don't believe that. I'm just going to give you a very simple example here. Here's a two-port network that consists of 3 1-ohm resistors. When we take Z open, in other words, we leave this terminal open over here, and we measure, put our ohm meter across it, we're going to measure 2 ohms because this is no longer connected to anything. 1 + 1 = 2. That's as deep a math as I'm going to get into here. So if we take a short circuit, though, this comes into effect, and we really have these 2 resistors now in parallel, and so that's a 1/2 ohm. Then we have 1 plus a 1/2 ohm, so our Z short is 1.5. So let's take the square root, multiply that together, that's 3. Take the square root, that's 1.73. And now our image impedance is 1.73 ohms. If we take that and put it on the output, and let's solve for the input impedance. So basically it's 1 ohm in series with 1.73, or 2.73 ohms. 2.73 ohms in parallel now. It's in parallel with 1 ohm. And all of you can solve that, but I've done it for you. That happens to be 0.73 ohms. So our input impedance is 1 plus 0.73 ohms, and magically here's our input impedance equivalent to our image impedance. This is really profound. I've always found this quite frankly fascinating, and you, in order to do this, you have to go through all kinds of calculations and everything. But here's where it's important to us. Excuse me. I have a Corona cough button here so that I can mute. Anyway, getting into it, let's imagine now that we take a very short piece of wire, and I'm talking maybe 3 inches, maybe an inch, a very short piece of wire, and we stick it inside of a conducting tube like this. Now, yeah, it kind of looks like a coaxial cable, doesn't it? All right, but yeah, let's hold off on that for a second. So the wire in the middle has inductance, because we all know that a length of wire will look like an inductor even when it's in free space. And we also know that the distance in between the 2 conductors, separated by a dielectric in between, there will be some capacitance. So we have an inductor and a capacitor in our little short segment of wire inside of a tube. And I can model that as a simple 2-port. Here's the inductor, and here's the shunt capacitance. Now, what's so amazing about this is that if you go through what we did before and did our open circuit, short circuit analysis of this network, like we did before, we find that the image impedance here, and I need to, in the limit, as we make this shorter and shorter and shorter, in the limit as the distance, as the length goes to 0, the image impedance goes to this formula. It's just L over C. The square root of L over C is the image impedance here. Now, I want you to notice, amazingly, that this is not a function of frequency, even though we have inductors and capacitors here. Somebody at the radio came up. Even though we have inductors and capacitors all over the place here, all the frequency components cancel out in the limit, and you're left with the image impedance is simply henries divided by farads. Take the square root, and you got your image impedance. Okay, where are we going with this? It's taken a while, but let's cascade all of these now. We have all of these little 2-port networks, and just like we did before, we're going to cascade them. But now we've calculated our square root of L over C, and that's our Z0. If we appropriately choose the L over C ratio, we can choose Z0 to be 50 ohms, or different dimensions. We can make it 75 or 33 ohms. And we start cascading it. If we put the Z0 at the end, we can cascade all these little 2-port networks. And by golly, it's going to be Z0 at the input too, just like we did with everything else, like all the other 2-port networks that we just been talking about. And by now, I think you've guessed that the image impedance is nothing more than our familiar characteristic impedance of our coaxial. Now, what's important here is that, and we know that in a coaxial cable, if we terminate a coaxial cable in its characteristic impedance, the impedance at the beginning of the coaxial cable will still be you will see with your little impedance meter, you will measure Z0 or the characteristic impedance. If you terminate it in something else, something else will appear here. But we have a way of measuring this, and now I'm going to show you what that actually means. Everything that I'm going to be talking about, this input impedance is everything to your VNA, because after all, it's pretty much all it does. It measures the input impedance, but it takes that number and it calculates return loss, it calculates SWR, it calculates the magnitude of the reflection coefficient. You don't need to know all of that stuff. Your machine will do it for you. But notice that I didn't talk anything yet about traveling waves, reflection coefficients, or SWR in order to get this concept that we have an image impedance that appears at the beginning. This is how a transmission line works. And let's go on to the next segment here and just kind of take a look at, once we cascade these into a transmission line, we can show, again, by doing our open and short circuit tests, we can show that the SWR on the line is exactly equal to the difference between your load resistance. In this case, as a special case, it's the division between the load resistance and the characteristic resistance of your line, and that is your SWR. So if you can measure that, you can calculate the SWR from your input impedance. That's an important thing to know. Input impedance and SWR are pretty much the same thing. It's not unique here, and I'll show you when we get into the Smith chart, but you'll see that if we had a 100 ohm resistor on the output over here, we're going to have a 2-to-1 SWR. Likewise, if we had a 25 ohm resistor over here, we'd still have a 2-to-1 SWR. As a matter of fact, when I show you on the Smith chart, you'll realize that there are actually an infinite number of impedances that'll give you a 2-to-1 SWR. And we'll get into that when we get into the Smith chart. So let's start talking about reflections and all of that kind of thing. We know that when we have an open circuit or a short circuit at the end of a transmission line, we get perfect reflections. We don't really have to know too much more about it than that at this point anyway. What I want to show you here, though, is that going back to that original slide of the network analyzer, they have down here, they have what they call the DUT, or device under test. Now they're showing transmission characteristics, so they've got both ports connected. But here's our transmit port that we're dealing, and here's our device under test. You can imagine this to be your antenna, for example, or an attenuator, or a filter, or something like that. Now, the important thing to consider is that this cable here, especially at high frequencies, is going to affect the impedance. It's going to transform this impedance into something different over here. But if we were to take our short circuit and our open circuit loads and connect them at this point, we can actually calculate the effect of this 2-port network. Here's, you can consider all your connection leads as a 2-port network, and we can actually calculate what the impedance would be here if we only measure the impedance here. So when we do this, we call this the reference plane, because in a sense, once you have this calibration point, you're actually measuring the impedance here. Even though you're measuring something different, the computer in here is taking this into consideration because you calibrated it out. It's actually subtracting out the effect of this 2-port network so that you can see at the reference plane exactly what your 2-port device under test is doing. And that's an important kind of thing. We can take any two-port network, once we've characterized it, once we understand it, and we've calibrated it with open and short circuit, we can calculate it out of our equation so that we could actually measure impedances through there as if the intervening two-port didn't even exist. So I'm going to add, I don't have it here, but there is some additional study that we can do. But I want to get into before the days we had when we measuring complex impedances at RF frequencies is very difficult to do. We could do it today in your little vector network analyzer, but in days past, it was a very difficult process. And in days past, when I was going to school, they made me do it this way.